friends, welcome back. When we throw a ball, it cannot vanish at some point and reappear someplace else to continue its motion. Thus, we perceive the path of the ball as an unbroken curve. In this session, we translate this concept into a precise mathematical formulation called continuity and develop some fundamental properties of continuous curves. We define continuity and discuss the ways to conclude whether a given function is continuous or not at a particular point. We will describe the intermediate value property of continuous function and use the same to answer the question why a continuous curve has no breaks or halts. Continuity of composition of function will also be discussed. Intuitively, the graph of a function can be described as a continuous curve if it has no breaks or halts. To make the idea more precise, we need to understand what properties of a function can cause breaks or halts in its graph. Referring the figures, we see that the graph of a function has a break or halt if any of the following conditions occur. First one, the function f is undefined at C as in figure 1. Second one, limit of f of x as x approaches C does not exist as in figure 2 and 3. Third one, limit of f of x as x approaches C exists, but its value is different from f of C as in figure 4. The above discussion suggests the following definition of continuity of a function at a point. A function f is continuous at x equal to C if it satisfies the following three conditions. First one, f of C exists, in other words, C lies in the domain of f. Second one, limit of f of x as x approaches C exists, that is, f has a limit as x approaches C. Third one, limit of f of x as x approaches C is f of C, that is, the limit equal the function value. If one or more of the conditions in the definition of continuity at a point fails to hold, then we say that the function has a discontinuity at that point. In the figure 5, the function is not defined at C, violating the first condition in the definition of continuity at C. In figure 6, the one-sided limits of f of x as x approaches C both exist but are not equal, and hence limit of f of x as x approaches C does not exist, which violates the second condition in the definition of continuity at C. We call a function like that in figure has a jump discontinuity at C. In figure 7, the one-sided limits of f of x as x approaches C are infinite. Thus, limit of f of x as x approaches C does not exist, which violates the second condition in the definition of continuity at C. We call a function like that in figure has an infinite discontinuity at C. In figure 8, limit of f of x as x approaches C exists and f is defined at C, but these two values are not equal, violating the third condition in the definition of continuity at C. We call a function like that in figure has a removable discontinuity at C. More generally, a function f is said to have a removable discontinuity at C if limit of f of x as x approaches C exists, but f is not continuous at x equal to C due to any one of the following reason. Either f is not defined at C as in figure 9, or because f of C differs from the value of the limit as in figure 10. The terminology removable discontinuity is appropriate because a removable discontinuity of a function f at x equal to C can be removed by redefining the value of f appropriately at x equal to C. What value for f of C removes the discontinuity? By looking at the graphs or from the definition of limit, we can see that f becomes continuous at C if we redefine f of C equal to limit of f of x as x approaches C. To illustrate this, we consider one or more example. For the function f of x equal to x square plus x minus 6 upon x square minus 4. Obviously, f of 2 is not defined and hence f is not continuous at x equal to 2. Let us examine whether f has a removable discontinuity at x equal to 2. We can write for x not equal to 2, f of x equal to x square plus x minus 6 upon x square minus 4, which is equal to x minus 2 into x plus 3 upon x minus 2 into x plus 2 equal to x plus 3 upon x plus 2. A rational function whose denominator is not 0 when we substitute x equal to 2. Thus, by substituting x equal to 2, limit of f of x as x approaches 2 is 2 plus 3 upon 2 plus 2 equal to 5 upon 4. As limit of f of x as x approaches 2 exists, but f of 2 does not exist, f has a removable discontinuity at x equal to 2. We remove the discontinuity by redefining f by denoting the new f in uppercase letter as follows. F of x equal to f of x if x not equal to 2, f of 2 if x equal to 2 equal to x plus 3 upon x plus 2. Graph of f and its continuous extension f are shown in figure 11 and 12 respectively. The continuous extension f has the same graph except with no hole at ordered pair 2, 5 upon 4. F is called the continuous extension of f to x equal to c. As observed in the example, for rational function f, continuous extensions are usually found by cancelling common factors. The function whose graph is shown in figure 13 is discontinuous at the origin because it oscillates too much to have a limit as x approaches 0. It does not fall into any one of the following categories: jump discontinuity, infinite discontinuity or removable discontinuity. One-sided continuities at a point. We now define one-sided continuity at a point. A function f is right continuous or continuous from the right at a point x equal to c in its domain if limit of f of x as x approaches c from the right is f of c. A function f is left continuous or continuous from the left at a point x equal to c in its domain if limit of f of x as x approaches c from the left is f of c. With the definition of one-sided continuities, we can say that f is continuous at a point x equal to c in its domain if and only if it is both right continuous and left continuous at the point. If and only if limit of f of x as x approaches c from the right equal to f of c equal to limit of f of x as x approaches c from the left. That is, if and only if limit of f of x as x approaches c is f of c. The step function graphed in figure 15 is right continuous at x equal to 0. Since limit of f of x as x approaches 0 from the right is 1 equal to f of 0. But it is not left continuous because limit of f of x as x approaches 0 from the left is 0.5 which is not equal to 1 which is equal to f of 0. Hence, f is not continuous at the point 0 also. Continuity at endpoints as one-sided continuities. In practice, most functions of a real variable have domain that are intervals or unions of separate intervals. For an interval open interval a b, the point A is the left endpoint, B is the right endpoint, and any point C such that A less than C less than B is called interior point. Continuity at endpoint is defined by taking one-sided limits. A function is continuous at the left endpoint A of its domain if it is right continuous at A. That is, f is continuous at the left endpoint x equal to a of its domain if limit of f of x as x approaches a from the right is f of a. Similarly, a function is continuous at the right endpoint b of its domain if it is left continuous at b. That is, f is continuous at the right endpoint x equal to b of its domain if limit of f of x as x approaches b from the left is f of b. But at an interior point c, a function is continuous if and only if it is both right continuous and left continuous at that point. That is, if and only if limit of f of x as x approaches c from the right is equal to f of c equal to limit of f of x as x approaches c from the left. That is, if and only if limit of f of x as x approaches c is f of c. As an example, consider figure 16 showing the graph of a function y equal to f of x whose domain is the closed interval 0, 4. Using the definition of continuity at endpoints and that at interior points, we discuss the continuity of f at the point x equal to 0, 1, 2, 3 and 4. F is continuous at the left endpoint 0 of its domain if it is right continuous at 0. That is, if limit of f of x as x approaches 0 from the right equal to f of 0. Here from figure it is obvious that limit of f of x as x approaches 0 from the right equal to 1 equal to f of 0. Hence, f is continuous at the left endpoint 0. 1 is an interior point of the domain. Limit of f of x as x approaches 1 does not exist as f has different right and left hand limits at x equal to 1. Hence, one of the condition in the definition of continuity at a point fails, and so f is discontinuous at the interior point x equal to 1. F is right continuous at x equal to 1 because limit of f of x as x approaches 1 from the right equal to 1 equal to f of 1, but not left continuous at x equal to 1 because limit of f of x as x approaches 1 from the left equal to 0 which is not equal to f of 1. F is discontinuous at x equal to 2 because limit of f of x as x approaches 2 equal to 1 not equal to 2 equal to f of 2. Moreover, f is not right continuous at x equal to 2 because limit of f of x as x approaches 2 from the right equal to 1 not equal to 2 equal to f of 2, and not left continuous at x equal to 2 because limit of f of x as x approaches 2 from the left equal to 1 not equal to 2 equal to f of 2. F is continuous at x equal to 3 because limit of f of x as x approaches 3 equal to 2 equal to f of 3. F is discontinuous at the right endpoint x equal to 4 because it is not left continuous at 4 as limit of f of x as x approaches 4 from the left not equal to f of 4. As another example, the function f of x equal to 1 upon x is continuous for any non-zero real number because for any real number c not equal to 0, limit of f of x as x approaches c equal to limit of 1 upon x as x approaches c is 1 upon c equal to f of c. At x equal to 0, f has an infinite discontinuity. Continuous functions. A function is called continuous if it is continuous everywhere in its domain. A function that is not continuous throughout its entire domain may still be continuous when restricted to particular intervals within the domain. For instance, f of x equal to 1 upon x is not continuous on the set of real numbers, but it is continuous on any interval not containing 0. Continuity on intervals. A function f is said to be continuous on an interval I in its domain if it is continuous at every point in the interval I. That is, if limit of f of x as x approaches c is f of c at every interior point c, and if the appropriate one-sided limits equal to the function values at any endpoints I may contain. We remark that a function continuous on an interval I is automatically continuous on any interval contained in I. Theorem: Continuity of algebraic combinations. If the functions f and g are continuous at x equal to c, then first one, sum and different rules. F plus g and f minus g are continuous at x equal to c. Second one, product rule, f g is continuous at x equal to c. Third one, constant multiple rule, k times f where k is any number is continuous at x equal to c. Fourth one, quotient rule, f upon g is continuous at x equal to c provided g of c not equal to 0. Fifth one, power rule, f of x to the power m upon n provided f of x to the power m upon n is defined on an interval containing c and m and n are integers. Polynomial functions are continuous everywhere. We now show that polynomials are continuous on every point of the real line. Let p of x be polynomial and let c be a real number. Since limit of polynomial at a point c is obtained by evaluating the polynomial by substituting x equal to c, we have limit of p of x as x approaches c equal to p of c. It follows that p is continuous at c. Since c is an arbitrary real number, it follows that p is continuous at every point of the real line. Also, since p is an arbitrary polynomial, it follows that polynomials are continuous on every point of the real line. As an interval is a subset of the real line, in particular polynomials are continuous on every interval. For example, f of x equal to x to the power 4 plus 20 and g of x equal to 5x times x minus 2. They are continuous at every point of the real line. Functions such as polynomial functions that are continuous for all real numbers, that is on the interval open interval negative infinity infinity, are said to be continuous everywhere. As f of x equal to x to the power 4 plus 20 is continuous everywhere, by power rule f of x to the power 1 upon 2 equal to x to the power 4 plus 20 to the power 1 upon 2 equal to square root of x to the power 4 plus 20 is also continuous everywhere. But though h of x equal to 9 minus x square is continuous everywhere, h of x to the power 1 upon 2 equal to 9 minus x square to the power 1 upon 2 equal to square root of 9 minus x square is continuous only on the interval closed interval negative 3 3, as square root of 9 minus x square is defined only on the interval closed interval negative 3 3. Continuity of rational functions. Let f of x equal to p of x upon q of x be a rational function and c be a point such that q of c not equal to 0. Then limit as x approaches c is obtained by substituting x equal to c in the rational function. That is, limit of f of x as x approaches c is f of c. Hence, it follows that f is continuous at c. It follows that every rational function is continuous at every point where its denominator is different from 0. For example, the rational function f of x equal to x to the power 4 plus 20 upon 5x times x minus 2, which is continuous at every point of the real line except x equal to 0 and x equal to 2, where the denominator is 0. Continuity of absolute value function. The function f of x equal to absolute value of x is continuous at every value of x. If x greater than 0, we have f of x equal to x, a polynomial. If x less than 0, we have f of x equal to negative x, another polynomial. Finally, at the origin, limit of absolute value of x as x approaches 0 is 0, which is equal to absolute value of 0 equal to f of 0. Continuity of trigonometric functions. From trigonometry, we know that the graphs of sin x and cos x are drawn as continuous curves. We will not formally prove that these functions are continuous, but we can motivate this fact by letting c be a fixed angle in radian measure and x a variable angle in radial measure. If, as illustrated in figure, the angle x approaches the angle c, then the point p cos x sin x moves along the unit circle toward q cos c sin c, and the coordinates of p approaches the corresponding coordinates of q. This implies that limit of sin x as x approaches c is sin c and limit of cos x as x approaches c is cos c. Thus, sin x and cos x are continuous at the arbitrary point c. That is, these functions are continuous everywhere. Then, applying the quotient rule of limits, limit of tan x as x approaches c equal to limit of sin x as x approaches c upon limit of cos x as x approaches c, which is equal to sin c upon cos c, which is equal to tan c, for any c for which cos c not equal to 0. This shows that tan x is continuous at every point where it is defined. Similarly, the quotients cot x equal to cos x upon sin x, sec x equal to 1 upon cos x and cosec x equal to 1 upon sin x are continuous at every point where they are defined. Limit of trigonometric functions. From the discussion above, for any c, limit of sin x as x approaches c is sin c, and for any c at which tan c is defined, limit of tan x as x approaches c is tan c. Similar discussion holds for other trigonometric functions. It follows that limit of a trigonometric function f as x approaches c is f of c, provided f of c is defined. That is, for a trigonometric function, limit of f of x as x approaches c is f of c, provided f of c is defined. An important trigonometric limit. Let us give the formal proof of the important trigonometric limit. Limit of sin x upon x as x approaches 0 is 1. First, we note that the formula for the area A of a sector with a radius r and a central angle theta radian is A equal to 1 upon 2 r square theta, equation number 1. This is obtained as follows. Referring figure, area of the sector upon area of the circle equal to central angle of the sector upon central angle of the circle, that is A upon pi r square equal to theta upon 2 pi. Hence, A equal to 1 upon 2 r square theta. In evaluating the limit, x is measured in radians. We first assume that 0 less than x less than pi upon 2. Hence, using A equal to 1 upon 2 r square theta with r equal to 1 and theta equal to x, the area of the sector of radius 1 and central angle x is x upon 2. Also from figure, the area of this sector lies between the area of two triangles, larger triangle with area 1 upon 2 into 1 into tan x equal to tan x upon 2, and smaller triangle with 1 upon 2 into 1 into sin x equal to sin x upon 2. Thus, tan x upon 2 greater than or equal to x upon 2 greater than or equal to sin x upon 2. Multiplying through by the positive number 2 upon sin x yields 1 upon cos x greater than or equal to x upon sin x greater than or equal to 1. Now, taking reciprocals, reverse the inequality. So, we obtain cos x less than or equal to sin x upon x less than or equal to 1. That is, cos x less than or equal to sin x upon x less than or equal to 1, 0 less than x less than pi upon 2, equation number 2. We now show that the inequalities in 2 also holds for negative pi by 2 less than x less than 0. Multiplying this inequality by negative 1, we obtain pi upon 2 greater than negative x greater than 0 or 0 less than negative x less than pi upon 2. So, by equation 2, cos of negative x less than or equal to sin of negative x upon negative x less than or equal to 1. That is, cos x less than or equal to sin x upon x less than or equal to 1, negative pi upon 2 less than x less than 0, equation 3. Since cos of negative x equal to cos x and sin of negative x equal to negative sin x. That is, we have now cos x less than or equal to sin x upon x less than or equal to 1 for negative pi upon 2 less than x less than 0 or 0 less than x less than pi upon 2, equation 4. That is, for negative pi upon 2 less than x less than 0 or 0 less than x less than pi upon 2 with g of x equal to cos x, h of x equal to 1, f of x equal to sin x upon x is sandwiched between g of x and h of x, where limit of g of x as x approaches 0 equal to limit of cos x as x approaches 0 is 1, and limit of h of x as x approaches 0 is limit of 1 as x approaches 0, which is equal to 1. Hence, by squeeze theorem, limit of sin x upon x as x approaches 0 is 1. The intermediate value theorem. A function f is said to satisfy the intermediate value property if for every a less than b in the domain of f and every choice of real number k between f of a and f of b, there exists c belongs to closed interval a b, that is in the domain of f such that f of c equal to k. By referring the figure, we get an intuition that a continuous function on a closed interval has intermediate value property. Bolzano's intermediate value theorem. Let closed interval a b be a closed interval and let f is a function from closed interval a b to R be a continuous function. If k is a number such that f of a less than k less than f of b, then there is at least one number c belongs to closed interval a b such that f of c equal to k. This theorem was first proved by Bohemian mathematician Bernard Bolzano in 1870. The continuity of f on an interval is essential to the Bolzano's intermediate value theorem. If f is discontinuous at even one point of I, then the theorem conclusion may fail as it does for the step function graphed in figure, which is continuous at every point on the real line except the point 0. At x equal to 0, there is a jump discontinuity. From figure, it can be seen that though k equal to 0.75 is a number such that f of negative 0.5 equal to 0.5 less than 0.75 less than 1 equal to f of 0.5, there is no number c belongs to closed interval negative 0.5, 0.5 such that f of c equal to 0.75. Why graph of a continuous function have no breaks? At the beginning of this session, we have observed intuitively that the graph of a function can be described as a continuous curve if it has no breaks or holes. Bolzano's intermediate value theorem justifies this observation. The theorem is the reason the graph of a function continuous on an interval closed interval a b cannot have any breaks. It will be a connected, that is a single unbroken curve. Finding root using Bolzano's intermediate value theorem. We call a solution of the equation f of x equal to 0 a root or 0 of the function f. For example, 5 is a solution of the equation x minus 5 equal to 0 and hence root of the function f of x equal to x minus 5. Similarly, 2 and negative 2 are roots of f of x equal to x square minus 4. The following version of the intermediate value theorem tells us that if f is continuous, then any interval on which f changes sign must contain a 0 of the function. Location of roots theorem, intermediate value theorem for finding root. Let closed interval a b be a closed interval and let f is a function from closed interval a b to R be a continuous function, and if f of a and f of b are non-zero and have opposite sign, then there is at least one solution of the equation f of x equal to 0 in the interval open interval a b. We prove this as follows. If f of a less than 0 less than f of b, then take k equal to 0. Then by Bolzano's intermediate value theorem, there is at least one number x belongs to open interval a b such that f of x equal to k equal to 0. Similar situation occur if f of a greater than 0 greater than f of b. This completes the proof. We use intermediate value theorem for finding roots to answer the question, is there any real number exactly 1 less than its cube? If there is any such x, then it must satisfy the equation x equal to x cube minus 1 or x cube minus x minus 1 equal to 0. Hence, we are looking for a 0 of f of x equal to x cube minus x minus 1. By trial, we find that f of 1 equal to negative 1 and f of 2 equal to 5. As f of 1 and f of 2 are non-zero and have opposite sign, we conclude from intermediate value theorem for finding roots that there is at least one number in closed interval 1 2 that is a 0 of the function. As another example, let us examine whether a root of x cube minus 9x plus 1 equal to 0 exists between x equal to 2 and x equal to 4 with f of x equal to x cube minus 9x plus 1. It can be seen that f of 2 equal to negative 9 and f of 4 equal to 29 have opposite signs. So, a root lies between 2 and 4. intermediate value property does not imply function is continuous. Converse of intermediate value property is not true. Though every continuous function satisfies intermediate value property, a function satisfying intermediate value property need not be continuous. For example, consider the function f of x equal to sin of 1 upon x when x greater than 0, 0 when x equal to 0. This function is not continuous at x equal to 0 because the limit of f of x as x tends to 0 does not exist if the function has the intermediate value property. Since a continuous function assumes all intermediate values, one may have a feel that the interval closed interval a b will be mapped to the interval closed interval f of a f of b. But this is not true, that is f of closed interval a b need not be a subset of closed interval f of a f of b. This can be seen from the following example. The graph of the continuous function f of x equal to x square negative 1 less than or equal to x less than or equal to 2 is given in the figure. Here with a equal to negative 1 and b equal to 2, we have f of a equal to f of negative 1 equal to negative 1 square equal to 1 and f of b equal to f of 2 equal to 2 square equal to 4. So, that closed interval f of a f of b equal to closed interval 1 4. Now, f of closed interval a b equal to f of closed interval negative 1 2 being the range of f when the domain is closed interval negative 1 2. We have f of closed interval a b equal to closed interval 0 4. This shows that f of closed interval a b equal to closed interval 0 4 is not contained in f of a f of b equal to closed interval 1 4. Characterization of intervals. So far we have encountered with various types of intervals. If a b belongs to R and a less than b, then the open interval determined by a and b is the set open interval a b equal to set of all x belongs to R such that a less than x less than b, equation number 1. The points a and b are called the endpoints of the open interval a b, but the endpoints are not included in the open interval. If both points are adjoined in the open interval, we have the closed interval a b equal to set of all x belongs to R such that a less than or equal to x less than or equal to b, equation number 2. The sets left close right open interval a b equal to set of all x belongs to R such that a less than or equal to x strictly less than b, equation number 3. And left open right closed interval a b equal to set of all x belongs to R such that a strictly less than x less than or equal to b, equation number 4 are half open or half closed intervals determined by the endpoints a and b. Each of the above intervals given in equation 1 to equation 4 have length defined by b minus a. If a equal to b, note that the corresponding open interval is the empty set. Open interval a equal to empty, equation number 5. Whereas, the corresponding closed interval is the singleton set, closed interval a equal to singleton set a, equation number 6. If a belongs to R, then the set is defined by open interval a infinity equal to set of all x belongs to R such that x greater than a, equation number 7. And open interval negative infinity a equal to set of all x belongs to R such that x less than a, equation number 8 are called open race or infinite open intervals. Similarly, the sets defined by left close right open interval a infinity equal to set of all x belongs to R such that x greater than or equal to a, equation number 9, and left open right closed interval negative infinity a equal to set of all x belongs to R such that x less than or equal to a, equation number 10 are called closed race or infinite closed intervals. In these cases, the point A is called the endpoint of the interval. It is often convenient to think of this entire set R as an infinite interval. In this case, we write open interval negative infinity infinity equal to R, equation number 11. and we do not consider any point to be the endpoint of open interval negative infinity infinity. An obvious property of interval is that if two points x comma y with x less than y belong to an interval I, then any point lying between them also belong to I. In other words, if x and y belong to an interval I, then the interval closed interval x y is contained in I. We now state that a subset of R possessing this property must be an interval. Characterization theorem for intervals. If S is a subset of R that contain at least 2 points and has the property that if x y belongs to S with x less than y, then closed interval x y subset of S, equation number 13, then S is an interval. We now state and prove that intervals are preserved by a continuous function. Preservation of intervals theorem. Let I be an interval and let f is a function from I into R be continuous on I. Then this set f of I is an interval. To prove this, let alpha beta belongs to f of I with alpha less than beta. Then there exists a point a b belongs to I such that alpha equal to f of a and beta equal to f of b. Further, it follows from intermediate value theorem that if k belongs to open interval alpha beta, then there exists a number c belongs to I with k equal to f of c belongs to f of I. Hence, closed interval alpha beta subset of f of I, showing that f of I possesses property given in equation 13 of characterization theorem for intervals. Therefore, f of I is an interval and this completes the proof. Composition of functions. We now consider an operation of functions called composition, which has no direct analog in ordinary arithmetic. Informally stated, the equation of composition is performed by substituting some function for the independent variable of another function. For example, suppose that f of x equal to absolute value of x and g of x equal to x square plus 1. If we substitute g of x for x in the formula for f, we obtain new function f of g of x equal to absolute value of g of x equal to absolute value of x square plus 1, which we denote by f composition g. Thus, f composition g of x equal to f of g of x equal to absolute value of g of x equal to absolute value of x square plus 1. In general, we make the following definition. Given function f and g, the composition of f and g denoted by f composition g is the function defined by f composition g of x equal to f of g of x. The domain of f composition g is defined to consist of all x in the domain of g for which g of x is in the domain of f. Limits of composition of functions. The following theorem will be useful for calculating limits of composition of functions. Theorem. If limit of g of x as x approaches c is L and if the function f is continuous at L, then limit of f of g of x as x approaches c is f of L. That is, limit of f of g of x as x approaches c equal to f of limit of g of x as x approaches c. This equality remains valid if limit as x approaches c is replaced everywhere by 1 of limit as x approaches c from the left or limit x approaches c from the left. As an example, if limit of g of x as x approaches c exists, nothing that f of x equal to absolute value of x is continuous everywhere, allow us to write limit of absolute value of g of x as x approaches c equal to limit of f of g of x as x approaches c equal to f of limit of g of x as x approaches c equal to absolute value of limit of g of x as x approaches c. In particular, limit of absolute value of x square plus 1 as x approaches negative 1 equal to absolute value of limit of x square plus 1 as x approaches negative 1 equal to absolute value of negative 1 whole square plus 1 equal to 2. The following theorem is concerned with the continuity of composition of functions. Continuity of compositions. Theorem: if the function g is continuous at c and the function f is continuous at g of c, then the composition f composition g is continuous at c. The proof follows from the fact limit of f composition g of x as x approaches c equal to limit of f of g of x as x approaches c equal to f of limit of g of x as x approaches c equal to f of g of c equal to f composition g of c. Using the continuity of composite theorem, being the composition of a polynomial with the square root function y equal to square root of x square minus 2x minus 5 is continuous at every x for which x square minus 2x minus 5 greater than or equal to 0. Being the composition of the continuous functions, cosine functions and x to the power 2 upon 3, cos of x to the power 2 upon 3 is continuous everywhere. Hence, by product rule, x cos x to the power 2 upon 3 is continuous. By sum rule, 1 plus x to the power 4 is continuous as the polynomial 1 and x to the power 4 are continuous everywhere. Then by quotient rule, y equal to x cos x to the power 2 upon 3 upon 1 plus x to the power 4 is continuous everywhere, since the denominator is never 0. The absolute value of a continuous function is continuous. Already we have seen that the absolute value function absolute value of x is continuous everywhere. Thus, if g of x is continuous at c, then by theorem on continuity of composites, the function absolute value of g of x, that is composite of absolute value and g of x, must also be continuous at c. More generally, if g of x is continuous everywhere, then so is absolute value of g of x. We summarize this as theorem: the absolute value of a continuous function is continuous. As an example, since absolute value of x minus 2 upon x square minus 2 is a composite of absolute value and a rational function x minus 2 upon x square minus 2, y equal to absolute value of x minus 2 upon x square minus 2 is continuous at every x for which the denominator is different from 0. Let us summarize the session. In this session, the definition of continuity and the way of examine whether a function is continuous at a given point are described. We have seen that the intermediate value property of continuous functions justifies the reason why a continuous curve have no breaks or holes. Continuity of composition of functions also has been discussed and illustrated through examples. Hope you enjoy the session. See you next time. Until